This video is about modeling a material, developing the constitutive relationship of a material based on thermodynamics, the laws of thermodynamics. To begin with, we're going to discuss the types of variables. We have three types of variables. The first of its kind is we call a free variable. Free variable is a variable that we can physically observe and do experiments and measure it. Suppose you were working with a material with stress, you can, strain, elastic strain. It's a free variable. The total strain that you can actually measure and see, that is also a free variable. We're going to denote our free variable by V. It is a set of all free variables, V1 dot 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 Vn. So our free variable is Vi, which is a function of position and time, where I, it runs from 1 to n. It's better not to call our free variable V. Instead, we call our free variable by F. And our total variable, all of the variables that would include free variable and other variables, we denote it by Vi. We're going to denote our free variable by F. Is a set of all free variable is lambda1 dot 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 lambda n. So the set of free variable is lambda I, the function of position and time, where I belongs to or runs from 1 to n. And here F stands for free. The feature of this free variable is that they are physically measurable, physically observable variables. Physically observable variables. The evolution equation of this free variable, which is denoted by lambda I dot, which represents the time derivative of lambda, delta lambda I over delta t, there is no restriction on it. It can be of any form. There is no fundamental restriction on it. The second class of variable that is of our major concern is the internal or hidden variables. These are the variables of the categories that of nature such that they are not physically observable, but they represent or models the micromechanical phenomena. We are going to denote this hidden variable or internal variable. We also call it internal variables by I, the simple I. It is a set of all the internal variables, alpha 1, alpha 2, alpha n. One of the most familiar hidden variable is the inelastic strain. And a less obvious one is back stress tensor that is used in modeling kinematic hardening models. We're going to come to that later, but for the time being, hidden variables are those that are not physically measurable or physically observable, and they represent the micromechanical phenomena that is happening under the hood. The evolution equation of this internal variable, alpha I dot, which is it represents the time derivative of alpha, is a function of position and time. There's a function that depends on the current value of the free variables and the current value of the hidden variable itself. This lambda and t, lambda and alpha, here we have to take the instantaneous value of this lambda and alpha at time t. So these are the instantaneous value at time t. This alpha It accounts for microstructural mechanism. Accounts for the microstructural mechanism. Another class of variable is dependent variable or associated variable. It goes by both of the names. Dependent variables. We denote the set of all dependent variable by D. D1, Dn. Here the subscript D denotes dependent. Index notation, we can represent it by the following fashion, where I runs from 1 to n. Here D represents dependent. So what is dependent variable? All the variables that are not free variable and hidden variable are dependent variable. So why these are called dependent variables? Because they depend on free variables and hidden variables. So di is a function of lambda and alpha. The evolution equation, we have a restriction on the evolution equation, we have a restriction on the form of the evolution equation, that is the rate or the time derivative of di is a function of lambda dot, and alpha. So here we can see that the rate evolution also depends on the rate of the change of free variable. We don't have any fundamental restriction on the form of free variable of the evolution of the free variable. Here I runs from 1 to n, where d represents dependent. So what we've seen that if V is a set of all variables that we are going to use to model our material, it is the union of the set of free variables, internal variables, and dependent variables. And this sets, this free variable, internal variable, and dependent variable are mutually exclusive. Mathematically speaking, we can write this mutually exclusiveness the following fashion. That means a variable cannot be both of two categories or three categories. If a variable is free, then it cannot be also hidden. If a variable is dependent, it cannot be free. So the intersection is an empty set. So let's model. Before going into that, let's take some concrete example. If we're going to model material, so what are the variables that we're going to work with? We're going to work with the mass density, or the stress, the strain, internal energy, Helmholtz potential, entropy, temperature, and a hidden variable. So how are we going to know what we're going to choose this hidden variable? Well, that depends on your experience with the problem that you're dealing with and the physical intuition that you've got. Those are the two things that will drive or guide you in the process. So here, the free variable is that one which is measurable. We can measure rho, and we can measure the strain. These are the two physically observable variables. So we're going to denote this free variable f is our rho and epsilon, the strain, for all rho dot, for all strain rate. Our internal variable is obviously this alpha. It takes account of the microstructural mechanism that is playing under the hood. There's a function. Remember that the evolution equation of alpha depends on the current state of the free variables and the current state of the hidden variable alpha itself. So it will be a function of rho, epsilon, and alpha. Next, we have our associated variable or dependent variable d. So the rest we have sigma is down, sigma, yes, sigma, no, rho is down, epsilon is down, our alpha is down. So rest of the variable, that is sigma, u, psi, s, and theta, these are the dependent variable. So sigma, u, psi, s, and theta, they are our dependent variable or associated variable. Here we can see that we have a potential psi, which is a free variable. So the free variable, we know that the form of the free variable is such that it depends on the state of the, sorry, it is not a free variable, sorry, my bad, it is dependent variable. So the dependent variable, if you go to previous slides, we can see that the dependable variable, the form is such that it depends on the state of the current state of the free variable lambda and the current state of the hidden variable. So dependable variable are those that functionally depend on free variable and hidden variable. So psi is a dependent variable, so it is going to depend on our free variable, that is rho and epsilon, and our hidden variable alpha. So psi dot, the evolution of psi with respect to time will be a function of psi, epsilon, alpha, rho dot, epsilon dot, alpha dot. But alpha dot again is the evolution of hidden variable that fundamentally depends on the current state of free variable, which is rho and psi, and the current state of the hidden variable itself. So we can see that it basically depends on sigma, rho, psi, epsilon, alpha, rho dot, psi dot. This alpha is again a function of alpha dot is again a function of alpha, so there is no this writing this alpha dot is redundant. So this the evolution of psi is not dependent on the evolution of alpha. Here, another dependent variable is our stress, which would depend on the free variable sigma, sorry, rho and epsilon, and the hidden variable alpha. And the evolution equation of rho, that is rho dot, which again depend, the functional dependency will be the same as psi dot, epsilon, alpha, rho dot, and epsilon dot. We are all set to dive into the discussion of how we're going to model, how we're going to model, develop a constitutive model of material. So the process goes roughly like this. So this topic is elements of a constitutive model, or elements of constitutive modeling. The process roughly goes like this, that first you have to define the free variables of the problem. So define the set of free variables that you're going to work with. Then choose the internal variables of the problem, or the specific problem that that is at your hand, at its disposal. What we're going to do here is to model, work with phenomenological model. So the internal variables, the only guide to choosing internal variable is your experience on working with that particular problem and your physical intuition. These are only the two guides that you have that will guide you to choose these two variables. So the choice of internal variables, I, then you have to define the corresponding evolution equation of this hardening or internal variables or hidden variables. So define corresponding evolution equation it is alpha I dot alpha I, which is a function of the free variable and the hidden variable. Then you have to postulate a specific form of the free energy. So again, this postulate of the form of the free energy, the only guide to that is your experience with the problem and your physical intuition. You have to define the form of the potential energy in such a fashion that it is able to describe the existing phenomena. So your result has to be consistent. So postulate a form of potential energy. We call it free energy. We denote it by psi, which is again a free dependent variable. So it will depend on the free variables, lambda, the internal variable, and it will depend on time itself. So this psi provides the constitutive equation through the dissipation inequality, the Clausius-Durham inequality. We get a constitutive equation from the psi. This psi is a potential. So if you take the derivative with respect to the variables, it can yield you the various forces, like stress. When you take the derivative with respect to strain, we're going to come to that later. So first, let's discuss thermoelastic materials. So it will be our this knowledge would be required if you want to constitutively model elastic material. So these are the prerequisite to diving into that discussion. So here we're going to discuss thermoelastic material, some rudimentary level of discussion on thermoelastic materials. For 1D, we know the Hooke's law is stress equals to a constant, which we call modulus of elasticity, times strain. So this equation is valid for 1D or one dimension. For 3 dimension, stress is a tensor. We have another fourth order tensor, C, contracted with the strain tensor, epsilon. In index notation, it takes the form sigma ij C ij KL, a fourth order tensor, times KL, epsilon KL. For isotropic elastic material, for isotropic elastic material, the C I J K L is of the form lambda. Here one is the fourth order isotropic tensor plus 2 mu times I. This lambda and I are called Lame constant. These are from the theory of elasticity. Lame constant. Sigma can be written in this fashion: lambda times transpose of strain plus 2 mu epsilon. In the index notation, we can write sigma ij equals to lambda epsilon kk delta ij plus 2 mu epsilon ij. Another thing that we need to know is the general form of fourth order isotropic tensor, that is ijkl takes the form in terms of Kronecker deltas ijkl plus ikjl, sorry, iljk delta L J K. Now we are all set to model a elastic material. So the title would be elastic material formulation. First step is to identify the free variable. Our free variable is the strain. So it is this elastic material. So this strain, it won't have any plastic part in it. So we have two parts in a strain. For a small strain, we can additively decompose it. One is elastic part and one is plastic part. This plastic strain would be zero. So the elastic strain and the total strain that you're going to observe are both the same for elastic material. Then you have to choose the hidden variable, which is the empty set. There is no evolution equation. So we don't need any hidden variable to model an elastic material. No evolution equation is needed. And the dependent variable is the stress and the free energy. Helmholtz free energy. Now, sigma dot, that is the rate of this dependent variable, is this free variable would be a function. This dependent variable would be a function of the free variable and the hidden variable. Function will depend on free variable and hidden variable. As the internal variable of the hidden variable is of empty set, so we don't have any hidden variable. So this dependent variable will be only a function of the free variable epsilon. Contracted with epsilon dot, and rho psi dot is the free energy. It will be a function of epsilon, the free variable again, dotted with epsilon dot. Now, then the next step is to define a potential, the form of potential. So we're going to postulate a particular form of the potential, a quadratic form, so to speak, which is again described in a pedagogical manner. So I'm going to just write this down, the form of the potential, which is half epsilon contracted with the fourth order tensor C, contracted with the second order tensor epsilon. So this is called the Helmholtz free energy. From the second law, Clausius-Durham inequality, we have this inequality, which is discussed in the previous video. We have derived that. Psi dot plus is theta dot plus sigma epsilon dot. So elastic body is basically a deformation of elastic body is basically an isothermal process. So we can drop this term because theta dot is zero. So the inequality reduces to the form sigma, minus rho sigma dot plus sigma contracted with epsilon dot greater than equal to 0 minus rho. Well, we have derived a form. We can see that we have expression for rho sigma dot. These are the two expressions that we can plug in. That is del derivative of rho psi with respect to epsilon times epsilon dot. That is derivative of minus derivative of rho epsilon. Sorry, rho psi with respect to epsilon dot plus rho contracted with epsilon dot greater than equal to 0 sigma minus delta rho psi delta epsilon dotted with epsilon dot greater than equal to 0 for all epsilon dot equal to f of epsilon equal to 0. Now we can, we can see that we have a theorem called the Coleman's theorem. The theorem goes like this, that if we have a function, the Coleman's function basically says that if you have a function, say f, what are you going to call? Suppose you're going to call this function g, I guess, or d. Let's call this function d, dissipation function. If we can write this in this nature, then this inequality is only true if my f of xy is 0 and g of xy is 0. This is called the Coleman's theorem. Coleman's theorem. So if we can drop one part, that is this part, then as you can see that the previous equation, we only had this term. The equation is equally valid. So as this equation happens to be of the form of this equation, and if you're going to drop this part out, the inequality also holds. So it will also imply that f of xy is 0. So we can write that this expression here is 0. So we can write that my rho minus derivative of rho psi of epsilon with respect to epsilon is 0. That is rho, which is a force basically, can be derived from the potential if you take that derivative of the potential with respect to the strain. This is essentially the mathematical definition of a potential. If you take the derivative of it with respect to a variable, that you're going to get a force. And so we have expression for potential that we have postulated, half epsilon contracted with the fourth order tensor c and with epsilon. So multiply it with rho and take a derivative, delta epsilon. What we're going to end up with is c dotted with epsilon. And the left hand side is sigma. So this is basically the Hooke's law. We have derived the Hooke's law for elastic material. Then we can go on and model thermoelastic material formulation. Thermoelastic material formulation. Let's do it in another video because it will get too much lengthy. So that's all for now.